Hello! Thanks for watching, and welcome to the next video in my series on basic statistics. Now, as usual, a few things before we get started. Number one, if you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit already. You're very smart and talented, but you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can work through it. I have faith in you. Many other people around you have faith in you. So should you. Number two, please feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. That way, when I upload a new video, you know about it. And it's always nice to connect with my viewers online. I feel that life is much too short and the world is much too large for us to miss the chance to connect when we can. Number three, if you like the video, please give it a thumbs up. Share it with classmates or colleagues or put it on a playlist. That does encourage me to keep making them for you. On the flip side, if you think there's something I can do better, please leave a constructive comment below the video, and I will take those ideas into account when I make new ones. And finally, just keep in mind that these videos are meant for individuals who are relatively new to stats. So I'm just going over basic concepts, and I will be doing so in a slow, deliberate manner. Not only do I want you to know what is going on, but also why and how to apply it. So, all that being said, let's go ahead and get started. So this video is the next in our series about simple linear regression. In our last three videos, we talked about the very basics of regression and introduced other fundamental concepts like the algebra of lines, general patterns to look for on scatter plots, and the least squares method. In this video, we're going to learn to evaluate how well a regression line fits the data it models. It is important to note that a regression model is unique to the data it represents. Adding or changing data points will most certainly change the regression model. The model is also only valid for the range of data points under analysis. It is not proper to extrapolate above or below the data being evaluated. So once a regression line is calculated, how much better is it than using only the mean of the dependent variable alone? To answer that question, we will have to calculate the sum of the squared residuals, or errors, much like we did in the previous video. However, this time we will do so using the regression line, not the dependent variable mean line. And finally, we will be able to quantify the fit of the regression model using a simple ratio or percentage called the coefficient of determination. So, if you are new to regression or are still trying to figure out exactly what it even is, this video is for you. So, sit back, relax, and let's go ahead and get to learning. So we can think of this video as a story. We'll call it a tale of two lines. Now in the first few videos we worked with this graph and data over here on the left. Now remember, in this case we only had the dependent variable, which is the tip amount at the restaurant. So we had 6 meals, and then we had the 6 tip amounts that are graphed on the y-axis in terms of their dollar amounts. Now we figured out that the mean of these 6 tips was $10. So we went ahead and put a line, a horizontal line, at $10. Then we found the errors, which is the distance from the mean line to each observed data point. And then we squared all of those errors and then added them up. When we did that, we came up with an SSE, or sum of squared error, of 120. Now this is a very important point. With only the dependent variable, the only sum of squares is due to error. That's all we have to work with. Therefore, it is also the total sum of squares and the maximum sum of squares for the data under analysis. So for these 6 specific data points, the total sum of squares will never be more than 120. So since the only source of error we have is the SSE, it's also the total sum of squares. In this case, they're the same thing. So SST is also 120, again, because in this case, they're the same thing. Now in the previous video, we actually went ahead and calculated the regression line using the least squares method. So we had the same 6 data points, the graph looks different because they're graphed differently, and then of course we have our regression line. Now in this video, we're going to do the same thing we did over here on the left. We're going to find the errors and square them and then add them up. But of course we will not be using the mean of the dependent variable to do that. We're going to be using the regression line to do that. Now, with both the independent variable and the dependent variable, the total sum of squares remains the same. It's 120 still, and it will always be for these 6 points. But ideally, the error sum of squares, or the SSE, will be reduced significantly because our line fits the data better. So the difference between the SST of 120 and the SSE, which we will calculate, is the SSR, or the sum of squares due to the regression we did. This is very much like ANOVA in a way. We'll talk about that as we go forward. But the SST will always be 120. We're going to calculate the SSE based on the residuals from the regression line, and then the difference between the SST and SSE will be the SSR, or the sum of squares due to regression. Take a step back and look. This is always what we are doing in simple linear regression. We are comparing a regression model over here on the right that we found using the least squares method to the case where we only have the dependent variable and the line is flat over here on the left. Now, if the model on the right we calculate looks a lot like the one on the left, and the sum of squared error is very high, then our regression model doesn't really do a whole lot for us. The idea is to reduce the SSE by having a line that fits the data better, because the better the line fits the data, the smaller the residuals, or the errors, will be. So this is our first case. You can go ahead and look at this again if you'd like, but we just took the residuals of the errors, squared them, and then added them up. This is 120. So having only the dependent variable, the best prediction for the tip of the next meal is just the mean of the tips, which in this case is $10. Since the mean line is flat, its slope is 0. So beta sub 1 equals 0. Again, this is just a review. Now in the last video, we actually calculated the regression line. So here's a regression equation at the top. And here's another one. Remember that Excel had a little bit different number for the intercept than we did just because of rounding, but basically they're the same thing. So a few things. Our slope is not 0. Our slope is 0.1462. And remember, we interpreted that as for every dollar the meal amount increases, the tip is expected to increase by about 15 cents. That's the slope of 0.1462. Then we also had our intercept down here on the left, which really for this problem isn't very meaningful. Now we also had the centroid. So remember, the centroid is the intersection of the means of both variables. So the mean meal amount was $74 and the mean tip amount was $10. And the centroid will always fall on the least squares line. And that can be very helpful if you have to find out other things about your graph. So now that we're done reviewing, let's go ahead and get to sort of the heart of the matter of this video. But to do so, we have to calculate the predicted values for each meal amount. So over here on the left, we have the observed total bill, which in like the case, the first meal was $34. And then we have the observed tip. So that was the tip that was actually received by the waiter. So the first one was $34. The tip that the waiter got was $5. $108 meal had a tip of $17, so on and so forth. Now, in this middle column, we have our actual regression equation. So 0.1462x minus 0.8188. Now that is what we're going to use to create the predicted tip amount using our regression equation for each of our meals over here in the red on the left. All we do is substitute each meal amount in for x, because again, that's our independent variable. So we go ahead and evaluate all of these equations, and that will give us our predicted tip amount over here on the right. So again, to substitute the meal amount, into the regression equation, and that will give us our predicted tip amount based on the regression. So substitute over, evaluate, and now we have our predicted tips. So for this meal that was $34, the waiter received $5. Now our regression equation would have predicted a tip of $4.15. Let's skip down. We had a meal that was $88. The waiter or waitress received $8. Now using our regression equation, we would predict a tip of $12.05. So you can see the observed tip amount is not always, or usually is not, the predicted tip amount that is given using the regression equation. So we have a discrepancy here. We have the observed tip amount and we have the predicted tip amount. And the difference between those two is going to be our error. So here is our data again. So the diamonds, the orange diamonds, represent our actual observed values for the tips that the waiter received. So here's our regression equation. Now, the purple dots are the predicted tip amounts for those meal amounts. And as you can see, they're not the same as what we observed. So for the first one, we had $4.15 that we would predict the tip to be. For the second one, we had a predicted value of $6.64 for a tip, and so on and so forth on up the graph. Now we have to find out what the error is, or what the residuals are. So again, that is just the distance between the predicted value and the observed value, because that's, quote, how far off our regression is from the actual data. So it's just the distance between the predicted and the observed. So now we have to find out what those errors are. And as you can imagine, it's simple subtraction. It's just the difference between the observed and the predicted that we calculated. So for our first meal, $34, we had observed tip amount actually in the restaurant of $5. Our regression predicted a $4.15 tip approximately. So the difference between those two was 0.8495, or about 85 cents. And that is the error for that meal amount. And then we do that for all 6 meals. Very simple, just subtraction. Now, of course, as we do with other errors, we have to square those differences. So the difference of 0.8495 for the first meal, if we square that residual, it is 0.7217. For the second meal, the difference is 2.0307. We go ahead and square that, and it's 4.1237, and so on and so forth. So we square each residual, just like we've been doing the past 3 videos, and then, of course, we add them up, because that is the sum of the squared errors. When we sum those up, we have an SSE that is 30.075. So, for our regression model that we came up with, our SSE is a little bit over 30, so 30.075. So on our graph, we take each residual, and then we square it, just like this. So we take the residual and square it. So these are areas we have here. And then, just like we did before, we go ahead and add those up. Now, let's compare the sum of squared errors from our 2 models. Now remember, in the first model, where we only had the dependent variable, which was the tip only, we had a sum of squared errors, or SSE, of 120. And again, remember, that's also the SST for that model, so 120. Now for our regression model, where we have the DV and the IV, so the dependent and independent variable, where the tip amount is a function of the meal amount, now we have a sum of squared errors, or SSE, of 30.075. See how this works? That's the entire point of simple linear regression, to create a model, to create a line through our data that reduces the SSE as much as it possibly can. So if we actually make these physically the same scale side by side, we can see that we put all those SSEs for the first model together, it's 120, Then we do the same thing for our regression model, and it's 30.075. So you can actually see the physical difference in the scale of the errors. So when we conducted the regression, the SSE decreased from 120 to 30.075. That is, 30.075 of the sum of the squares was explained or allocated to the error in the regression model. So instead of having 120 as the error, as in the first case, we reduced that to 30.075 because we reduced the distance from the regression line to the data points. Where did the other 89.8925 go? Well, 89.925 is the sum of squares due to our regression. SST equals SSR plus SSE. In this case, SST is always 120, and that equals 89.925 plus 30.075. So here are our two models again. So the first one, our SSE, was 120, and of course the SSE and SST are the same for that model, so the SST is also 120. Now in our second regression model that we did, our SST again is still 120, but now the SSE is 30.075 because of the reduced distance between the regression line and the observed data points as it compares to the one over here on the left. So doing simple subtraction, we had 120 minus 30.075. That gives us our SSR, or sum of squares due to regression, and that's 89.925. So now that we have the SST, the SSR, and the SSE, we can go ahead and talk about the coefficient of determination. So, how well does the estimated regression equation fit our data? Now this is where regression begins to look a lot like ANOVA. The total sum of squares is partitioned or allocated into SSE and SSR. And hopefully at some point I'll do a separate video on the relationship between regression and ANOVA. But it's all about allocating or partitioning the total sum of squares into two or more things. In this case, SSE and SSR. So the total sum of squares is split. Some of it goes to SSR, some of it goes to SSE. So if the SSR is large, it uses up more of the SST, and therefore SSE is smaller relative to the total. The coefficient of determination quantifies this ratio as a percentage. So the coefficient of determination has the variable r squared equals SSR divided by SST. So it's the sum of squares regression divided by the total sum of squares. And if you actually do this in a statistical software package, regression will actually give you back an ANOVA table, just like you saw when you did an ANOVA. So we're going to have SS and mean squares and an F statistic and a significance level and everything just like we did in ANOVA. And of course, in this case, this is the actual ANOVA for the data what we're working with. We can see that the F is very large and significance is 0.0258, which is significant at the 0.05 level. So there is a relationship between linear regression and ANOVA, because it's all about partitioning or allocating the total sum of squares into different components. And then we measure the ratio of those components to figure out whether or not the model is statistically significant. Same idea. So how do we interpret the coefficient of determination? So again, it's SSR over SST. In this case, it's 89.925 divided by 120. So we go ahead and do that division, and we come up with 0.7493, or 74.93%. Because remember, the 120 is the total, so 89.925 of the 120, that's a percentage, and that is 74.93. So we can conclude that 74.93% of the total sum of squares can be explained using the estimated regression equation to predict the tip amount. The remainder, so 25.07%, is due to error. And again, that's based on this regression equation we used, where X is the dollar amount of the bill. So it's really about partitioning the total sum of squares as a percentage, saying, hey, this percentage belongs to SSR, and this percentage belongs to SSE. And then we can develop a model that says this fits well or does not fit well. In this case, it is a good fit. So a coefficient of determination of 74.93% is good. And we also saw that in the ANOVA table, which was statistically significant. So it's all about partitioning the total sum of squares into SSR and SSE. And we want SSE to be as low as possible for the model to be considered a good fit and for the ANOVA table to produce a significant result. So let's put it all together on one graph. So you can see here we're dealing with 3 data points for each measure on our x-axis or independent variable. So if we look at this one here sort of to the right, we can see that we have a orange diamond, we have a black circle, and a purple circle. So 3 data points that represent that meal of $88, I think it was. So remember that the diamond is the actual observed value. The black circle is the mean of the dependent variable, which was the tips, which is $10. The purple circle is the predicted tip amount based on the regression model. So each meal kind of has 3 reference points: the observed, the mean of the dependent variable, and the predicted value. So the first square difference to look at is the SSE, and I think it's the easiest to remember. So it is the sum of the squared differences between y sub I, which is the observed value, the diamond, minus y hat sub I, which is the predicted value, which is the purple circle. So we take the difference of each one along the graph, we square them, and then we add them all up. And that is the SSE for our regression model. So it's the distance between those two, and similarly those two up here. So the difference between the observed, the diamond, and the predicted, the purple circle. Now the next one is SST. It's the sum squared total. Now it is the sum of the squared difference between each observed value, which is the diamond, minus the mean of the y-axis, or the dependent variable, which is y bar. So the difference between those, then we square it, then we add them all up. So that's the difference between the observed and the mean. So the orange diamond and the black circle. So just like that, and just like that there. And of course the final one is SSR. So it is the sum of the squared difference between y hat sub I, that's the predicted, that is the purple circle, minus y bar, which is the mean of the dependent variable. So we find the difference, we square them, and then add them up. And that is this distance here and this distance here. And of course, we would do this for each point along the graph. So it's always a relationship between these 3 points that represent each value of the independent variable. So in the middle here, in this case, an $88 meal amount, we have the observed, we have the mean of the y's, and we have the predicted. And we have 3 relationships going on between those 3 data points. And the squared differences among those 3 data points is actually the total sum of squares package of SST, SSE, and SSR. So now you can see what it actually looks like on a graph. Okay, so that wraps up our video on simple linear regression, fit, and the coefficient of determination. So remember, this is all about a comparison, a tale of 2 lines, where we had the one graph where we only used the mean of the dependent variable, and then we had our regression equation and that graph over on the right, and it's always a comparison between the two. If the regression model isn't any better than the mean of the dependent variable, then the model doesn't really give us anything new, and it will most likely come back as statistically insignificant, the SSE will be very high, and then we will just move on from there. But it is always a comparison between these two different models. Now, the coefficient of determination just tells us how we allocate the total sum of squares in the regression model. So it's split. It's either SSE or it's SSR. And we hope for a good fitting model that the SSE is very low and the SSR is very high. But in either case, their sum will always add up to SST, whatever that happens to be. So I look forward to seeing you in that next video. I wish you all the best of luck in your studies and in your work, and I look forward to seeing you again next time.